Okay, so let's look at this last problem. They've given us this logistics model. Logistics does not mean logarithmic. So be very careful. There are two different things. By the way, I don't even see the word log in here. So this is a logistics model. Got it? Okay, so let's look at this last one. They've given us this logistics model. Here's something you need to be aware of. Logistics does not mean logarithmic. As a matter of fact, I don't even see the word log in this particular function. It's a logistics model, and they've told us that this represents the population of a certain bacteria in grams. Okay? All right, and then they've given us a few questions to look at. So the first question wanted to know the carrying capacity. Well, here's the thing. If they want to know the carrying capacity of this particular bacterium using this model, what you need to understand is they're saying, hey, what is the most amount of bacteria that this particular area can hold for this bacteria? You've heard of the Old West and their ghost towns? Well, the reason with their ghost towns is because the people had busted out of the resources that were available because they got to their limit, shall I say, and then they had to move on because they exhausted their resources. Same situation. Now, here's what's going to tell us how to figure out the carrying capacity. What I need to look at is as time marches on. So what I'm actually going to focus on is this part right here. As time marches on to infinity, okay? As time keeps getting larger and larger and larger. Got it? Okay, so first off, let me just look at this e raised to a negative power. That negative power implies that this should be written as a fraction. Agreed? And yes, you're going to have to remember your fractions. So this is really what I'm dealing with, is I'm dealing with this fraction down here. Now, we are going to look at the limit as time marches on, as time goes to infinity, of this particular fraction. And my question to you is this. As time moves on, as time gets larger, what happens to this exponent? It keeps getting larger, right? Okay, so as it keeps getting larger, then e to a large power becomes extremely large. And so 1 over an extremely large number, it keeps getting smaller and smaller and smaller, doesn't it? Till it eventually looks like the limit of this is 0, isn't it? Okay, so that means that this part is basically, I should say, just put an arrow, marching on to 0. So this e to this negative power is basically going to 0. 0 times 33.6 would be 0. 0 plus 1 is 1. 3,000 divided by 1 is 3,000. Here's your carrying capacity. Is 3,000 grams of this bacterium. That's all that this atmosphere can hold. That's all that this area, I should say, can hold for this particular bacterium based upon this model. Cool? It has to deal with us understanding this e to the negative power, realizing to write it as a fraction, and then looking at the limit of it as time goes to infinity. Because 1 over a large number gets smaller and smaller and smaller, right? As your denominator increases, the whole fraction decreases, and it eventually becomes 0. Cool? Okay, so that was part A. Part B wants to know the growth rate. Well, it's a rate. And the rate is right here in the exponent of the e, which makes sense because that's where we find the rate normally. Now you're like, why do they call it a growth rate when it's a negative number? Well, because it's negative, it really doesn't belong here, does it? I know we wrote it as a fraction, but if you multiply, it goes to the top, doesn't it? So in this particular example, our growth rate is 36.5%. So be careful. I know it was negative, but it was in the denominator, which means it really belongs in the numerator. So be careful about that. Let's see what part C is. C wants to know the initial population size, right? Well, the initial population means time is equal to 0. Agreed? So look at it. If t equals 0, and let me get some of this out of the way so you can see it just a little bit better. If t equals 0, what's 0 times that negative number, right? That's 0. What's e to the 0? Yeah, e to the 0 is 1, isn't it? So for us, we're really working on 3,000 divided by 1 plus 33.66, and this becomes a 1, this e, doesn't it? And when you punch that into the calculator, you get approximately 86.6 grams, depending on how many decimal places they ask you to round. Cool? Okay. Let's look at part D. Part D wants to know the population after 9 hours. So we get to plug in that 9, don't we, for T. So it's always a good idea to write the formula out so you can see what it is you're plugging into, or what the formula looks like. So when you're plugging it into your calculator, you have a better idea. Times 9. Okay, so I already did my work, and I ended up with approximately 1,327.3 grams. Hopefully we agree. Got it? Okay, and then they gave us 2 more questions, didn't they? They want to know when the population is going to be 700 grams. Well, I need some board space. But as I'm getting some board space, answer me this. What does it mean when the population is 700 grams? What variable are they looking for? What variable have they given us? Yeah, they're asking when, which means I'm looking for time, which means I must know the end. And the ending population for this bacterium is 700. So for part E, we have 700 grams equaling this lovely fraction. Now I put the 700 over 1, and what I did was I basically cross-multiplied. Because I would have 700 times this lovely fraction equaling 3,000, wouldn't I? So I am just going to do this. 700 times this lovely fraction equaling 3,000. This lovely denominator, I should say. And then I'm going to divide both sides so I can get this denominator by itself. Why do I want it by itself? Because I'm trying to solve for that t that's in the denominator. Got it? Okay. I'm going to subtract the 1 from both sides. And when I did that, and yes, I reduced this fraction as well. Okay? And no, I'm not going to give you a decimal, because I need things to be exact. So this fraction is 30 over 7, isn't it? I minus 1, I get 23 over 7. this fraction reduced to 30 over 7. And then I minused 1, which is 7 over 7. So for those of you who need a little refresher on your fractions, there you go. And then I have to divide both sides by this 33.66, don't I? You know, most of this stuff, most of you get how this problem works. Your challenge is sometimes doing the algebra. Well, that's why I'm making certain I write it out. With me? And then you get to take the natural log of both sides, don't you? Well, wasn't that just lovely? But it's not unexpected. You guys already know that. This wasn't unexpected. And then you get to divide both sides by that decimal, don't you? So here's the thing. I'm not going to show it, but you know you have to divide both sides by this negative decimal. So for me, after I did that division, I got time is about 6.4 hours. So it's going to take about 6.4 hours for this bacterium to reach 700. Good? Okay. And then they gave us one last question. And they wanted to know about half the carrying capacity. They want to know how long is it going to take for the population to reach half of the carrying capacity. So we got to go back to part A, don't we? Part A gave us the carrying capacity. What was the carrying capacity? Yes, it was 3,000. So half of that, excellent. Half of that would be 1,500, wouldn't it? So let me ask you this. In this last question, or this last part, what variable are you looking for? You're looking for time, which means you better know the ending amount. Do you know the ending amount? Yes, you do. The ending amount is 1,500, isn't it? So, part F, my ending amount is 1,500, equaling this 3,000 over this lovely denominator. Okay, so part F almost looks like part E, doesn't it? I'm going to do that cross multiplying again, which means I'm going to get 1,500 times this lovely denominator, equaling 3,000. And then I'm going to get the denominator by itself by dividing both sides by the 1,500. With me? And 3,000 divided by 1,500 is 2. Yay! Minus the 1 from both sides. Divide by the 3366. And then you end up having to take, no surprise, the natural log of both sides. And then you have to divide by that negative 0.365 on both sides. Agreed? So when you do that, I end up with the time being approximately 9.6 hours. So, we've talked about a variety of exponential growth and decay models, including Newton's law of cooling, which is a decay model, including this logistics problem at the same time, which, in a way, even though this looks like a negative, is actually a growth model. Because if you have a negative exponent on the bottom, that means this thing belongs on the top. So, I would suggest playing this over again, pausing it where you need to, and as always,